Steady state exercise part 2. Data would show that there will be an increase in rate of perceived exertion until 3 to 4 minutes, and then it should stay around the same once steady state exercise has been reached, as they shouldn't be working any harder or easier. For Josh, there was an increase between 4 to 10 minutes, which is normal. However, Josh's RPE continued to increase until 16 minutes, which shows that he wasn't working at a steady state. From 4 to 16 minutes, Max's RPE dropped from 14 to 10, and Summers remained between 16 to 14, which shows the plateau that should be seen at a steady state, and between 16 to 20 minutes, both of their results stayed the same. This shows that they were able to work at around the same level of energy and steady state was achieved. However, some of the results don't link to other data, so the participants might not be telling the truth about how hard they were working. During steady state exercise, there should be an initial increase in breathing rate at the start of exercise, and then there should be a plateau when the body is able to keep up with the demand for oxygen. For Max, there was a small rise in breathing rate from 40 to 46 at 8 minutes, and then there was a slight plateau until 20 minutes as his breathing rate stayed between 46 and 42, which shows that he was working at a steady state. However, this doesn't correlate to his other results, so the data for his breathing rate might be unreliable. Josh's results also show a small increase in breathing rate from 26 to 34 at 2 to 4 minutes, and then it remains between 34 and 30 until the end of the exercise, which is what should happen compared to normative data, as the plateau shows that he was working at a steady state. However, Summer's results were different as her breathing rate kept increasing until 16 minutes, from 24 to 37, and then decreased to 30 at 20 minutes, which shows that she was not working at a steady state. Post 1 minute to exercise, both Josh and Summer's breathing rate decreased, but Max's remained at 42, which could suggest that he was working anaerobically because he might have had an oxygen debt, so it didn't decrease as fast as Josh and Summer's. In my hypothesis, I said that heart rate will increase at the start of the exercise but will then plateau when the heart is able to keep up with the demand for oxygen. This is a null hypothesis. Our method to measure the changes in the cardiovascular system was to measure heart rate every 2 minutes by a participant checking the athlete's pulse for 30 seconds and then multiply it by 2. Normative data would show a large increase in heart rate from beginning of exercise to around 4 minutes, where it should plateau until the end of the exercise if the participant is working aerobically and at a steady state. In our results, we can see that Summer's data was the same as normative data, as there was an increase in heart rate until 4 minutes due to changes in the body which cause receptors to send signals to the CCC, which send impulses through the sympathetic nervous system and secretes the hormone norepinephrine to stimulate the SA node to increase heart rate. Then there was a plateau as our heart rate remained between 173 to 178 from 8 to 20 minutes, which supports my hypothesis, as there was an initial increase in heart rate at the start but then plateaued until the end. This plateau occurred because the heart was contracting at the right pace to pump enough blood to the working muscles to give them oxygen for respiration, so they were able to keep going at a constant speed. Max's results also showed an increase in heart rate until 8 minutes, and then it plateaued from 185 at 8 minutes to 173 at 20 minutes, which shows that he worked at a steady state, but normative data would normally show a plateau at 3 to 4 minutes, which could be because he was working too hard at the start. For Josh, the piece of equipment broke which was meant to tell us his heart rate, so we had to use an experimental method, which is why his results were not the same as normative data. In my hypothesis, I said there would be an initial rise in breathing rate until 3 to 4 minutes because receptors in the body would send signals to the respiratory control center, and more specifically the VRG, where the ECC will send impulses through the phrenic nerve to the external and internal intercostal muscles, depending if it's inhalation or exhalation, and this will allow the ribcage to lift up and out or down and in for forceful breathing. Once enough oxygen is getting to the muscles, there should be a plateau. As this prediction is the same as normative data, it is a null hypothesis. We measured breathing rate by observing the athlete as they breathe through their nose and out their mouth, so it was easier to see each breath. For Josh and Max, their breathing rates increased from 2 to 4 minutes and then remained between 4 breaths per minute until the end of the exercise, which is because their tidal volume increased to allow enough oxygen to dissociate into the bloodstream so it can be used for aerobic glycolysis at the working muscles. This means that they were able to keep a steady breathing rate as they were using oxygen at the same rate as they were supplying it to the muscles. For Summer, her breathing rate was 24 at 2 minutes, but kept increasing to 37 at 16 minutes, which is because she may have been working too hard for her body to keep up with, so she had to breathe faster in order to get more oxygen. However, experimental methods were used and her data could be inaccurate. In my hypotheses, I said that there would be a small decrease in O2 saturation as the oxygen will be used up faster than it is being supplied at the start of the exercise because the intensity of the exercise is increasing. But then O2 saturation should plateau because the aerobic system will be used after 3 minutes of exercise. Normative data would also show this, so it is a null hypothesis. We measured the athlete's O2 saturation by using an oximeter. At the start of exercise until 4 minutes there was little to no changes, and Josh's O2 saturation actually got higher from pre-1 minute, which could be because we got that results after his warm-up. However, at 8 minutes we start to see some small decreases and then their data started to plateau, which could show that the aerobic system was being used as there was still a high amount of oxygen in the body and they were able to maintain this through the exercise. However, at 12 minutes, Max's O2 saturation dropped from 97 to 83, which could show that the aerobic system was not being used at this point, as he might have started to work too hard and used up a lot of oxygen, or the data could be wrong due to a malfunction with the equipment used. The data we got was not exactly what I expected it to be, as I thought there would be a larger decrease at the start of exercise, but this might be because they weren't working as hard as they were at around 8 to 12 minutes. Do you accept your hypothesis? For the cardiovascular system, I accept my hypothesis for this because other than Josh's inaccurate data, which was because of an experimental method, the other athletes' data were the same as what I predicted would happen to heart rate during steady state exercise. For the respiratory system, I accept my hypothesis because Josh and Max both show an increase until around 4 minutes and then a plateau, which is what I predicted would happen, but Summer's data was not what I expected. For energy systems, I don't accept my hypothesis because O2 saturation didn't decrease initially until 4 to 3 minutes, but there was a small decrease at around 8 to 12 minutes followed by a plateau, and all of the athletes had higher O2 saturation, which shows that the aerobic system was being used and a steady state was achieved by Josh and Summer.